So thanks again for everybody for joining. You might be just logging on if you didn't participate this morning. We are going to be talking about dissolved oxygen and temperature. My name is Tamara Lipsey, and for those of you who might not know me, I work for the Department of Environment, Great Lakes, and Energy. I've been with the department for 18 years. Some of you might be wondering, where is Marcy? Marcy does dissolved oxygen. Marcy's still with EGLE, but she is in a different position now and has some different responsibilities. So I have taken over for her, and I'm really excited to do that. Since I've worked at EGLE a long time, I worked with Bill Diamond and Ralph Bednarz, both back when they were the MiCorps coordinators. So I have familiarity with the program, but this is allowing me to be a lot more familiar with the program and learning things about it that I did not know previously, and working with a really great new team of people. So I'm enjoying that, and I will enjoy meeting all of you and getting to work with the public more. The picture on the right here is me in my dining room, getting the dissolved oxygen meters ready for you all. So that was the first thing I learned to do. So we are going to, this is a little bit of a view of where we're going to go today. First, we're going to talk about why dissolved oxygen and temperature are important. And then we'll go over our dissolved oxygen temperature program here in MiCorps. Then I'll go over the equipment that you're using and the procedure you will use. And then we'll wrap up with what happens at the end of the sampling season. So what does dissolved oxygen and temperature measure? Obviously, temperature is what we use to see how warm or cold it is out there and how warm or cold it is in the water, maybe to see if the water's warm enough for you to swim yet. And then dissolved oxygen is just what it sounds like. It's the oxygen that's dissolved in the water, and it's what is available for aquatic organisms to use. We breathe the air, aquatic organisms use oxygen in the water to breathe. So why is it important? Well, there's many physical, chemical, and biological components that are impacted by dissolved oxygen and temperature. And the next few slides and videos will explain a little bit more about that. And then we'll return back to this slide and this question later in the presentation. So first I want to talk about thermal stratification, and then we'll watch a video to give you a visual of what thermal stratification is. So by measuring temperature, you can determine how a lake stratifies. And what that means is, how does it go into these little different layers that I'm showing here? This is a diagram of the common temperature profile of a lake in the summer months here in Michigan. The upper layer of the water is warmed by the warmer air temperatures and the sun. The sun has a lot to do with how warm the water gets. And this area is called the epilinium, and it includes this littoral zone over here, which is that area near shore where plants grow because sunlight can reach the bottom. The wind helps keep this upper zone fairly similar in temperature. There isn't a lot of difference in temperature there in that epilinium. The next zone is called the metalimnion, and it includes an area we call the thermocline, which is where temperature suddenly decreases. The metalimnion is usually a thinner layer than the epilinion. And then deeper lakes in temperate areas like where Michigan is, where we have colder winters, they often separate into these layers, and the bottom layer is called the hypolimnium, which is the coldest layer. And that is where the water is the most dense or the heaviest, and the water is much colder down there. So as I noted, water is heavier when it's colder up until 4 degrees Celsius, and then it actually starts to become lighter and rise to the surface, where it might then freeze when it reaches 0 degrees Celsius. I'll talk a little bit more about that later, but I want to watch a video to get a visual of what this stratification looks like. Oh.
Imagine you're swimming at the lake on a hot summer day, and your friend says, "Hey, I bet you can't touch the bottom." And you're like, "I bet you I can." So you take a deep breath, and you swim down and down and down, and suddenly it gets cold and you stop. What is this? What's going on? You've just experienced something that's hugely important to everything that goes on in the lake. It's called stratification. After you get back to the surface and catch your breath, you think, why is it warm up here but cold below? Is it always this way? Let's run an experiment and find out. What we have here is a model of a lake cut in half down the middle. We've taken all the warm water, dyed red, and moved it to one side. The cold water, dyed blue, is moved to the other side. In the middle is this barrier that keeps the sides separate. Now let's remove the barrier and watch what happens. As you can see, there's a lot of movement between the two layers as they come together. But look, the warm water has settled out on top. Let's try the experiment again. This time we put the cold water on the left and the warm water on the right, just to see if it makes a difference. Once again, the warm water settles out on top. What's going on? To answer that, we need to take a look at the physical principle driving the whole show: density. Density is the amount of stuff in a given volume. In our case, that stuff is water, and that volume is this glass beaker. This beaker is filled to the brim with our cold water. Let's see how much it weighs. $166.2 grams. Now we've emptied the cold water and refilled the beaker with the warm water. And the warm water weighs in at 165.1 grams, a little bit less than the cold water. We can calculate the density of these two samples by dividing the mass by the volume. First, we need to correct our previous measurement by subtracting out the mass of the empty beaker. This gives us 116.2 grams for the cold water and 115.1 grams for the warm water. Now we divide by the volume of the beaker to get a cold water density of 1.00 grams per milliliter and a warm water density of 0.99 grams per milliliter. In reality, it's a very small difference, but that small difference has a big impact. It allows the warm water to essentially float on top of the cold water, and it keeps the two layers from mixing together. So what affects the temperature and in turn the density of the water in the lake? You might think the temperature of the air surrounding the lake is the answer, but really the biggest impact comes from the sun. As sunlight enters a lake, it warms the surface water, making it less dense and lighter. As the surface water begins to float on the cold water below, a transition zone forms where it changes from warm to cold very quickly. We call that the thermocline. Remember, thermal stratification in lakes is as ordinary as the changing of the seasons, and in fact, it does change with the seasons. But we'll save that for another time. For now, know that warm water, cold water, and a thing called density set the stage for the behavior of, well, really everything that goes on in a lake. It's very important.
Okay. So hopefully that was really helpful for you all to see what visually happens to a lake during the summer in Michigan, in many of the lakes in Michigan. And that's here on this upper left-hand side. So then now I want to look at what happens during the other parts of the year. So over here we have the fall. And in the fall, as you all know, the temperature begins to drop and the wind begins to blow harder. And those cooler air temperatures and the sun is behind the clouds a lot more, especially here in areas of Michigan. And so the fall wind and all those cooler temperatures cool the top epilimnion air and mix. And that colder water, since we just learned, will start sinking to the bottom. And this pushes the warm water up, and this process is called turnover. And Eric talked about this earlier today. This is when the temperature from top to bottom is pretty similar, and the oxygen and the nutrients from the bottom are pulled to the top, and they're pretty similar as well. And then as it starts to get colder and colder, we move into winter, and the water keeps getting cooler on top until it reaches 4 degrees Celsius. And then when it gets colder than 4 degrees Celsius, it actually moves to the top. And so the water is colder on the top than the bottom of the lake during the winter, and eventually it can freeze. And this is really important, even though it's just a few degrees difference between the top and the bottom. That allows our fish to stay alive underneath there in the water. In the spring, the ice melts and it all reaches 4 degrees Celsius again. And then that's when it's its heaviest, and then the surface of the water warms up again. So turnover happens again because of that change in temperature. And in areas of the country where they don't have winter, this turnover effect can happen many times a year, or at least a few times a year, depending on what the weather is like. So I have one more video for you to show you. We're going to switch gears and talk a little bit about dissolved oxygen. I really like this neat video, and it explains it way better than I could. So we're going to watch it.
Imagine a world where we weren't surrounded by air. Without the oxygen in the air that we breathe, we wouldn't survive very long. But what about animals underwater? They need oxygen too. Where do they get it? The answer is from the water, because water actually also contains dissolved oxygen. Dissolved oxygen is just what it sounds like. It's oxygen that's dissolved in water. What does it mean for something to dissolve? If you've ever mixed sugar in water, you've noticed that the sugar seems to disappear. But what really happens is that the molecules of water mix with and surround the sugar molecules, breaking up the large sugar granules to make a sugar-water mixture. More specifically, since the parts of the mixture are spread out equally and evenly everywhere, we can call this mixture a solution. So when we say that something dissolves, it just means that it goes into an evenly distributed mixture called a solution. Now, like those sugar molecules, oxygen molecules also mix evenly with water molecules to form a solution. In other words, oxygen dissolves in water. But how does the oxygen get there in the first place? Well, there are two main ways that oxygen can enter a body of water, like the ocean or a lake. One way is from the atmosphere, or the air around us. Oxygen makes up about 1/5 of the atmosphere, and these oxygen molecules are constantly bumping into and entering water. Even more oxygen enters water through photosynthesis. You probably know photosynthesis mainly as the way that plants around us feed themselves. But there's actually a whole slew of other photosynthetic living things aside from plants. From tiny green bacteria called cyanobacteria to little phytoplankton with crazy names like dinoflagellate and even crazier bodies. All these creatures can produce food through photosynthesis. But in doing so, they actually also produce oxygen, which then dissolves in the water. What happens to this dissolved oxygen? Remember that like us other living things, the animals, plants, phytoplankton, and bacteria living underwater also take up oxygen to live. Furthermore, oxygen molecules are continually shuttling back and forth between the atmosphere and the water. But note that there's always at least some amount of oxygen that stays dissolved, and this amount depends on water conditions like the saltiness and temperature of water, and how much dissolved oxygen there is compared to the oxygen levels in the air. Now, why does the amount of oxygen already dissolved in the water and the surrounding air matter? Well, it's the same principle as walking into a crowded room from an empty hallway. You don't want to go in, and the people inside are trying to get out. In the same way, if there's more oxygen in the water than in the surrounding air, then the oxygen moves to the roomier atmosphere. Or if there's more oxygen in the air, then the oxygen moves to the water. The principle is the same for the saltiness of water. If you've ever tasted seawater, you know how salty it is, and that's because there's salt dissolved in seawater. Well, those salts are also taking up space in the water. You can imagine that as adding even more people to your crowded room, and the more people there are, the less room there is for you. So the saltier it is, the less space there is for dissolved oxygen. What about temperature? Well, when things heat up, they start moving around. Imagine yourself in a crowded room again. As everyone starts jostling around, it's a lot easier to move out of the room. Again, it's the same for dissolved oxygen. The oxygen molecules warm up and they start vibrating, making it easier for them to escape the water. So let's sum that up. Dissolved oxygen enters water from the atmosphere and from photosynthesis, and then gets taken up by living things or exits into the atmosphere depending on water temperature, saltiness, and the amount of already dissolved oxygen. Now you're probably thinking, who cares what the amount of dissolved oxygen is? Well, remember that living things need oxygen to live, and the more oxygen there is, the more animals can live there. So scientists measure dissolved oxygen to find out how healthy a body of water like a lake or a river is. But animals also adapt to the amount of dissolved oxygen. Fish like salmon need a lot of oxygen so they can only live in colder places, but fish like catfish can live in warmer waters because they need less oxygen. If you've ever wondered why the kinds of fish are different in different places, this is one reason why. Unfortunately, even these fish die off at very low oxygen levels, and humans have been decreasing freshwater oxygen levels in a process called eutrophication. Eutrophication is a big word that just means adding a lot of nutrients good for growing, like nitrogen and phosphorus, to a lake or a river, usually by pollution. That causes a lot of plants and cyanobacteria to bloom. Aren't plants good though? Don't they produce dissolved oxygen? Well, yes, but when they die, they sink to the bottom of the lake and decay there, and this decay uses up all the oxygen in the lake. With no oxygen to breathe, the fish and other animals die and the lake becomes unhealthy. So throw your trash properly and recycle. Together we can preserve our marine and freshwater ecosystems.
So I really like that video, except for the fact that they say it's not going forward. I'm trying to make it move forward. Except for they say that recycling although it's great, don't get me wrong, I recycle, it's not going to help your eutrophication issues in your lake. And eutrophication issues are not just from humans. It's a natural process. It's just human by adding nutrients to lakes, we're speeding up that eutrophication process. So your DO meter isn't going to look exactly like this, but you will be getting a meter to measure the DO and temperature in your lake. So oxygen, I did want to summarize the points, some points, good points from the video. Oxygen enters the water through air or by photosynthesis. The amount of salt and the temperature of the water can impact the amount of dissolved oxygen that's in the water. Too much algae or cyanobacteria can lead to the low dissolved oxygen levels, because even though they create dissolved oxygen, they use up oxygen when they die. And nutrients do speed up the addition of nutrients does speed up the eutrophication process. So understanding DO levels in your lake is one more tool to understanding the health of your lake. And so we're back to this slide where I started with why DO and temperature, why is it important? And it's affected by and does affect many physical and chemical and biological properties of a lake. It helps you define where the thermal layers in your lake are and helps classify your lake as warm or a cold water lake. It helps you can, by knowing that information, it determines what type of fish you can have in your lake, because different fish depend on different dissolved oxygen levels to survive. And the DO levels can be an indicator of nutrient release that might help and help with determining the trophic state of your lake. So this is what a dissolved oxygen and temperature profile looks like when it's graphed on some graph paper, and you'll get something just like this. In the graph, you can see that the dissolved oxygen, which is the circles, if you come down here, it stays right around 9 milligrams per liter until you get to about 20 feet. This is the depth of the lake. And then it starts decreasing after that. And then once you get past 30 feet, it really gets low and it's less than 1 milligram per liter. And most fish, well, pretty much any fish won't really live at that low of a dissolved oxygen level. Warm water fish species need 4 to 5 milligrams, so they would be found probably down to here. And cold water fish need as much as 8 milligrams per liter. This graph over here is the triangles, and this is the temperature. And so you can see that the temperature stays right around 20 degrees Celsius, which is 68 degrees Fahrenheit. And so similar to DO, it stays that until about 20 feet. And then it suddenly starts decreasing in temperature more quickly. And then it evens out eventually around 50 feet at a chilly 8 degrees Celsius, which is 46 degrees Fahrenheit. So using this information, we can see where the temperature is pretty warm and stays pretty similar. That's your epilimnion. And then where it's changing quickly, that's your metalimnion in your thermocline. And then where it stays colder, that's your hypolimnion. So once you enter your data into the database, as Paul went over this morning, you'll get reports to help you look at the profiles of your lake. We give you that graph paper so you can look at it ahead of time, but when the reports are developed, you'll get this information. So Lotus Lake is in Oakland County, and it's similar to the graph of Spider Lake I just showed you a minute ago. It's a pretty good example of a warm water lake here in Lower Michigan later in the summer. It's in September, and it's stratified just like the two prior examples I gave you. The numbers over here are the trophic state numbers for that lake, and I'm not going to go into this information a lot during my presentation, but it's just to show you that the dissolved oxygen and temperature information is one more piece of the puzzle to get the story about the health of your lake. Here's another example. This one's in Marquette County in the Upper Peninsula, Lake Independence. It's a pretty shallow lake. You can see it only goes to a little more than 20 feet, maybe 25 feet. And because it's shallow, it's able to maintain a constant temperature and dissolved oxygen level from top to bottom. The wind and the shallowness of the lake is just enough to keep it similar and doesn't have that thermal stratification. And the final example I wanted to show you was Higgins Lake in Roscommon County. The temperature you can see stays pretty stable down to about 40 feet. And then there is a thermocline and it keeps dropping as it gets deeper and deeper. It's a very deep lake. It gets to 100 feet deep or maybe even more. 100 feet might be as far as the cable goes. The dissolved oxygen number does something really a little bit more unique than some of the warm water lakes we have here in Michigan. It stays the same down to 40 feet, but then what actually happens is it increases. And that's because it's cold enough and there is not a lot of nutrients in this lake. So the lower nutrient level means that less plants and algae and there's less productivity. And so they're able to remain high because the temperature is colder down there, which allows for more dissolved oxygen to stay in solution. And Higgins Lake would be classified as a cold water lake, and it could support cold water fish species like cisco or trout. I don't know that it has those in there, but it could support them. All right, so that was a lot of intense science stuff. We're going to switch, go from to a different part of our brain now and talk about the dissolved oxygen and temperature monitoring program here in the CLMP and how it works and what equipment you'll be using. So everybody is going to need a meter if you want to participate in this parameter. You can borrow a meter. We have about 25 meters and we should be getting a few more. But because of that, you might need to share with 1 to 3 other lake groups. They'll be somewhere close nearby and we'll match you up, but then we'll leave the sharing logistics up to you. I wanted to note that if you are sharing meters this year, a lot of our cleaning protocols with COVID has been using a lot of the bleach wipes, the Clorox wipes. And we've been using them a lot in the office. I don't go to the office very often, but when we do go, it's to use the printer or the copier. And we just got a note that people, by using the Clorox wipes on the printer, have ruined the screen. And so if you are sharing a meter with somebody else, I urge you not to use Clorox wipes on the meters. We would rather you just practice good hand washing and keep our meters in good shape. You can also purchase your own meter. If you do decide to do that, my understanding is they're around $1,000 a piece. That includes the cord that has the sensor on it and the meter. But talk to us prior to purchasing it because we will let you know which type to buy. As soon as we get a better idea of how many lakes are going to participate in this parameter, we'll get the meters out to you as soon as possible. You'll be measuring dissolved oxygen twice a month from May through September. So if you know that you are going to want to do this parameter, please try to sign up soon so that we can start dividing them up. So we have 2 types of meters that we use. We have YSI 550As, which is this grayer one on the one side, and then we have Pro 20s. The 550As have the cord that you drop down into the water with the sensor at the end directly attached. You can't detach them. The Pro 20s have a cord that detaches, which is just sometimes nice. That junction can stay safe by being able to remove the cord. Or if we if the cord breaks, we can just replace the cord and the whole unit doesn't need to be replaced. Regardless of what meter you receive, they'll come in a storage box. The dissolved oxygen probe and cable, and the cable length is dependent on how deep your lake is. So we do have a couple of really long cables that we give to the lakes that are really deep. They'll come with batteries already inside and they'll be ready to go. And we'll include some spare batteries as well. But I believe they sat all last year and a lot of them still had no battery issues. So the batteries last quite a while. They'll also come with an agreement letter that you are acknowledging that you're borrowing the meter and that you will return it to us at the end of the sampling season. And it comes with a quick start calibration card of how to calibrate your meters, and I'll get to that a little bit more later. And they also come with extra dissolved oxygen membrane and solution, which I will get to in just a minute. So here's just another view of the 2 meters. The 550A, here's the cable, and it comes wound on the spool to keep it organized and keep the knots out of it. It has a weight on it to weigh it down so it goes straight into the water column. And then this is the probe at the end with a plastic cover on it to protect it. With the Pro 20s, the probe is a little longer, it looks a little different. A lot of them don't have the weight on them because this itself is much heavier than with the 550As, but they still come with a cord that's wound around a spool. So this shows a close-up of what the sensor looks like. This plastic guard can come off, but you should not ever need to remove that unless you need to replace the membrane cap. You should not need to replace that when you get them, because I have been doing that in my dining room this spring. So it should be ready and set to go. They are yellow now, this membrane cap, it's not a gray color. And then this little probe right here measures the temperature. So this measures the dissolved oxygen and this measures the temperature. The probes look a little different between the 2 different meters. Like I said, this one is like metal instead of the black plastic. So the Pro 20s, this is heavy, which is good because it helps it sink easier. Both of them have a cap like this. You can see in the cap of the 550A yellow sponge, and that's important. It needs to be damp at all times. Not standing water. So this is not full of water. It just needs to be damp to the touch. So just a few drops of water. So during the summer, if yours starts to dry out, just put a few drops of water in there to keep it moist. And the gray one, you can't see through it, but it has a sponge as well. So now you need to, now that you see what the equipment looks like, we're going to talk about sampling a little bit. So first, just like the other parameters, you want to make sure you have calm and dry weather conditions. You want to keep safe. Keeping you safe is more important than data collecting. So pack up your equipment, including your safety equipment, and grab a friend for both safety and to help with data recording. It's always nice to have company. Check your quick reference procedure checklist, which you'll receive if you sign up for this parameter. Make sure you have all your data forms, which will be included in your kit. And if you have a Pro 20, just make sure that your cable is connected to your meter. And then if you have a 550A, you're going to need to turn on your meter for 15 minutes. The Pro 20s don't require that. They're just, the mechanics are different. But with the gray ones, you need to make sure you allow them to warm up for about 15 minutes before you calibrate them using the quick start guide. And now I'm going to show you 2 videos of how to calibrate your meters. First, we're going to start with the calibration of the Pro 20. This video is to show you how to calibrate your YSI Pro 20 dissolved oxygen and temperature meter. It's really pretty simple. First, you want to check inside the cap that covers your probe and make sure that the sponge that's inside is wet. Always want to keep the environment for the DO probe moist, but it shouldn't be standing water. You just put that back on and then turn the unit on. You'll see at the top here, there's 2 measurements. One says milligrams per liter, mg/L. One says percent. The percent is the percent saturation, how much oxygen is in this container right now. And then the milligram per liter is what you'll be measuring when you put the probe into your lake. The temperature units are in degrees Celsius, which is what you want. And to calibrate, really all we have to do is hit this button here, press it, and then hold for about 3 seconds. And then it will say calibrating percent dissolved oxygen until it says calibration successful. And then you're all set. Notice it did go away, the calibration successful. So if it's taking some time and you look away, you might miss that. But if you wanted to double check, all you do is hit calibration again, hold it, calibration successful, and you're ready to go. Have fun. So I did want to note before I go to the next one that what calibration is, because I didn't really talk about that. So what we're doing is we're telling the meter, okay, when it's in air, it has a lot of oxygen. So the percent saturation of oxygen is really high. And so that gives it a starting point. And things when you turn it off and jostle the meter, it can throw that calibration off. So that's why it's important every time you go out to calibrate your meter. So next we'll watch calibration of a 550A. Hello, this video is to show you how to calibrate your YSI 550A dissolved oxygen and temperature meter. If you have a YSI Pro 20, there's a separate video for that. The first thing to do is to turn on your unit and then let it set for about 15 minutes. I've already done that. The next thing you want to do is make sure that the sponge inside your probe cap is moist. There shouldn't be standing water, it just needs to be slightly wet. If it's dry, make sure you put a couple drops of water in there and then replace the cap. The next step in calibration is to hit both the down arrow and the up arrow at the same time. When you do that, you will get CAL for calibration. You then hit enter. Once you hit enter, a number will come up. This is where you will enter the elevation of where your lake is. In the Lansing area, the elevation is about 900 feet. So there's a 9. However, if I was somewhere else and the elevation was, let's say, 700, I would put the down arrow twice to get to 7. If it was 1,000, I would move it up a couple to get it to 10, and so on. Once you have the correct elevation, hit enter again, and your unit will begin calibrating. It'll jump around quite a bit. Mine is not, because I have had this meter on for a while and it's had time to stabilize already. So you can see it's just jumping between 0.2, 0.1 to 0.2, 94.1 to 0.2. Your percent saturation should be between 93 and 98%. If it's not, keep waiting, and if it still does not, then you'll need to turn it off and try again. But since we seem to have a stable number, and it is between those numbers, I press enter. The next thing that comes up is the percent salinity. We have fresh water in Michigan, so we don't need to worry about this. So just make sure it says 0 and hit enter again. And there you go. You're all set. Before you go out and measure dissolved oxygen in your lake, however, you need to change the units from percent saturation to milligrams per liter. And you do that just by hitting the mode button once, and it changed to milligrams per liter. I see it's in degrees Celsius, which is what you want for the data sheets that we give you. If it says degrees Fahrenheit, all you need to do is hit the mode button and the down button at the same time, and it will change to Fahrenheit. Hit it again, both the arrow, down arrow and mode, and it will change back to degrees Celsius. Now you're all set. Have fun measuring your dissolved oxygen in your lake. Okie dokie. So those videos will be, they're not yet, but they will be available on our webpage for you to refer back to. And I think on the website right now, there are these presentations so you can print them out. So what I did is at the end of this presentation, which I won't show you today, there's some still frames of those instructions from the videos, but I do think the videos are maybe more helpful since we can't get together and go through it together. So there is also in your kit some kind of container, maybe an old film canister like this, maybe a Tylenol bottle I've taken the label off of, something to keep it, your extra membrane cap safe. And then it comes with this solution that needs to go in the membrane cap before you screw it back on. I have a video how to replace a membrane as well. I just don't have time to go through it today, but that will be available online. But if you are calibrating your meter and it doesn't calibrate, first check your quick start calibration guide that's with your kit. There might be something small. There's a lot of steps, especially with a 550A. There might be something you're forgetting. If you're not forgetting anything and you've turned it on and back off, you're sure you had it on for a long period of time, and you tried a couple of times and you can't get it to work, call me and I'll see if I can help you out. If I can't help you out, then you might have to replace your membrane. We only give you one, hoping that this won't be needed, but if it is, we do give you one. But again, it's only needed if your monitor won't calibrate. It will come with a brand new one. So you have calibrated your meter and you're ready to go. So you'll proceed to your sampling location, which is the deepest spot in your lake, just like all the other parameters. You'll anchor upwind, drift over it. Make sure you're at the depth that you need to be at with either your depth finder or a weighted line or your Secchi disc. Don't use your DO probe to check the depth of your water. We don't want to get mud and grime into the membrane. They're easily damaged. So just please don't do that. Turn on your meter, Make sure it's warmed up. Take the cap off that has the sponge in it, but leave the guard on it, whether it be the silver guard or the black plastic guard. And then you'll start at 1 foot deep for your first measurement. So you'll just unspool your cord and go to 1 foot deep. So this is what your data sheets look like. It has the same information that the other data sheets have at the top with the latitude and longitude, your lake name, etc. The bottom part of the first page has weather conditions, the depth that you're sampling at, and then circle which model you have, either a 550A or the Pro 20. And then if you're using one of our meters, write down your meter number, which will be written in a couple different places on it. If it's your meter, just write our meter on it. And then we need the calibration values only if you're using the 550A. So the Pro 20 is able to determine the lake elevation based on barometric pressure. But the 550As don't have that. So you, with your kit, if you get a 550A, we'll give you what the lake elevation is. We find it online for you. But we want you to enter that in so that we know that you calibrated it and know the elevation for where you're at. And then also put in what the percent air saturation was when you calibrated. And it needs to be, this says between 93 and 103. So I'll have to double check that. Well, maybe somebody can note what that's supposed to be in the chat. And then there's a space to give me also an outline of your lake. It doesn't need to be a work of art, just the general shape of your lake and then where you did the sampling at. This is page 2 of your data sheet. So it has the depths on the left there, and then temperature in percent Celsius and the dissolved oxygen. And you're going to take both those measurements at every depth noted there. So in the beginning, because temperature and dissolved oxygen doesn't generally change in the epilimnion zone, you're only measuring it at 1 foot, then 5 feet, 10 feet, 15 feet. And then at 15 feet, that's where some lakes might start to stratify. And so then we move down, we take depths, we take measurements at more frequent depths. So every 2.5 feet instead of every 5 feet. And it continues that way until you reach 2 to 3 feet above the bottom if you have a shallower lake. Or if you have a real deep lake, starting at 45 feet, you'll go back to every 5 feet because by then you're most likely in the hypolimnion. Take your last measurement a couple of feet above the bottom so you don't get the sediments into the probe like I noted earlier. If it does happen, because accidents do happen, just when you get it back to the boat, just gently swish it around in the lake to clean out the mud as best as you can. And when you're done with your measurements, you will put the plastic sleeve with the sponge back onto the guard and store it in your box. And this is that same graph you saw earlier with when you get back to your home, you can plot out the dissolved oxygen temperature. We'll give you several pieces of graph paper to be able to do this. And at some point, I hope to maybe make a video of how this is done in case you haven't done something like this before. Now, this is the point in class where I wish we were in person because we would practice measuring dissolved oxygen and temperature in a bucket of water in the classroom. But since we can't do that, I just want to go over taking a measurement a little bit. So you're going to start at 1 foot deep, like I said. You're going to move the probe with a slight jiggling motion. That's just to make sure the water is going by the probe. The dissolved oxygen reading will drift at each depth. So this can take some time, especially if you have a deep lake, because you have to wait every time you move it for that dissolved oxygen reading to stabilize. And you're going to mark it down to the tenths. So for this reading on this slide, it says 5.72, so you would mark 5.7 on your data sheet. Then you go to the next depth and just repeat the jigging motion. And remember to stop a couple feet above the bottom to protect the probe. This is on your data sheet, just a reminder to enter your data online at MiCorps.net and to make sure you return the data sheets to us by the end of October. So the end of the year return for the meters, you can return them, and we would prefer you return them with your last water chemistry sample drop off. If you forget for some reason, call me and we'll arrange a drop off date by October 31st. Especially right now during the pandemic, there might not be anybody at the office, so we have to make sure that somebody is going to be there. And make sure to keep your sponges damp even after your field season is over. Just make sure it keeps it damp, but no pooled water. And with that, there's not a lot of time for questions, but there's some time. And this is my contact information, which is also on our website. And it's located on top of the box you get. It's located on the quick calibration guide inside. So please call me if you have any questions. I'm happy to answer them.
Thanks so much, Tamara. You know, the one thing I miss about, being in person is that typically we get to have a little bit of applause and, congratulations for the speaker, and instead it's very quiet. But we did have a couple of questions come in while you were talking, but we knew that this was a lot to cover in an hour. So we tried to cover a lot of those in the chat, but there are a couple that have come in right at the end, and we do have a couple minutes. So, and this one, Tamara, I think is a good question for you. How often are these meters sent out for verification or certification?
We don't send them out unless they're not working, but the reason we have you return them to us is because there are some maintenance things that have to be done. The probe gets corroded because the way electricity works, it attracts like the minerals that are in your lake to the probe. So I have to sand them down and make sure the batteries are fresh, make sure there's no battery leak. So I go through all of that before we send them back out. And so this year there were 9 of them that weren't calibrating correctly for me. So I sent them in. 4 of them, they were able to calibrate, so they'll come right back. And then the rest of them need to be fixed, and we'll have to determine if we're going to do that.
That's a great point, Tamara. And Tom Tissue mentioned something that he's learned from some years of experience doing this on his lake. He says it might be worth mentioning the boat needs to be reasonably stationary so the wire remains vertical. And I know I've been on boats on windy days where we've tried to measure it, and it's hard to keep it at a certain level in the lake. It bounces around a lot.
Yeah, and if I give you one that you don't have enough weight on yours, we do have more weights that we can give you. If for some reason it's not, I don't know, maybe you have a really windy lake, because I know some lakes in Michigan are that way. Just let me know and we'll figure it out.
Yeah, and that might even be an issue if you have a lake that, has a lot of flow in it, right? So like an impoundment or something, where there might be a bit of a current down in the depths of the lake, something with a little more weight might help. That's a great idea. All right, well, it looks like we've gotten through all the questions right on time, Tamara. So thank you so much for going over that. I love those new calibration videos. Those will be a great addition to our MiCorps website.
Thank you, everyone. I hope to meet you soon.